Welcome to the Bergman Forum, everyone. All right, is that mic working? Thank you for coming. And we will. So we've got a new schedule for this semester, and you can pick up your schedules for this semester to put on your fridge, your notice board, or whatever at the front there. There's also free tea and coffee, as always. And as always, you're welcome to bring your lunches. So we've got a really exciting schedule lined up this semester with presentations from many different disciplines. I'll make one announcement, and that is that next week, Bob Myers, one of the great champions of the Bergman Forum and a veteran presenter, is giving a talk entitled Groundhog Day, Candlemas and Super Bowl XLV 111, Prophecies Large and Small. That's 48, right? And today we're very happy to have David DeGraff, also a champion of the Bergman Forum and a veteran presenter, and he's going to give us a tale of two telescopes. Thank you, David.
Okay, thanks for coming, everyone. So this is a really exciting time to be an astronomer. There at Alfred, there are two fantastic new telescopes that are out. Most people have heard of the James Webb Space Telescope. And let me see if I can get this floating window out of the way here. Oh. Got one of them out. Okay. This was launched on December of 2021, and it became active in July that year. It's a fantastic new telescope that is going to produce amazing results, and I'll talk about some of them that it's going to be doing. This is the new telescope at Alfred. It was delivered in 2019. Students started using it in 2021. There's a few things that happened in between there that got in the way, but they're basically the same. We've got a mirror down here. The starlight hits the mirror, bounces off a secondary mirror at the top, and goes through a hole to the instrument panel that's kept in the back. Our telescope has a mirror. Starlight comes in, bounces off this mirror, bounces off the second mirror here, goes through a hole and down to the instrument panel in the back. It's the same thing. Totally. Yes. So the James Webb Telescope was built to be the successor for the Hubble telescope. It was in the planning stages before the Hubble telescope even launched. I remember seeing papers when I was in grad school called Space Telescope, the Next Generation. There are a lot of Star Trek fans. Come on, go forward. So this is going to give, the Webb is going to give us a much clearer view than the Hubble did. Yes. All right, I have to click. They were both installed, and one of them was a little bit more exciting when it was installed. You've got a rocket launch over here, and you've got a big crane, and it's lifting the telescope up and moving it in through the open slit of the dome. That was really exciting and really nerve-wracking. And then there's a rocket launch.
And we have engine start.
Yeah. There were large teams involved in the installation
liftoff from a tropical
the
rainforest to the
telescope.
edge of time itself.
Yeah, I had some video screens in case it didn't. The video didn't play. I like this view looking down from the slit. So there are a lot of people involved in getting the Hubble telescope here. Here it is, life-size model of it. And there are a lot of people that helped install the telescope here as well. All right, so the Hubble was the first big space telescope. The Webb telescope, JWST, is looking in the infrared spectrum, which is a color of light we cannot see. So all of these, radio, microwave, infrared, all the way up to X-rays and gamma rays, those are all different colors. I call visible light one color and infrared's another color. So why are we bothering looking into the infrared? Here's a couple images from an infrared camera that hooks up to my phone. Here's some deer in my backyard. The dark patches here are the little bit of snow that was left in the spring. Snow is really cold, so it's not glowing much. The deer are warm and they are glowing. This is a heat duct in my house, shining, blowing hot air onto a chair and making that glow. And you can tell that the wire is turned on because the electricity flowing through it is heating it up. And here are students in a physics lab. This is the back of a computer monitor, glowing because it's warm. Warm things glow in infrared. And so that's why we're using this for the Hubble. We have a bunch of filters that we use to make color images. We're doing exactly the same thing on the Rosing telescope up at the observatory, except the colors that we're using up there are the ordinary red, green, and blue, mostly. Here, we're taking a bunch of different infrared colors, and the shortest of those infrared colors we color blue, and the longest we color red. And if we want to get some finer detail in there, we have narrow filters where we can match up the colors to the wavelengths they're looking at and get really spectacular images. Yeah. So here's all the individual colors that the Webb took for one of its early images. You don't need to see that. And here's what it looks like when we put them all together. Space images are never real. They never show what you would actually see. What you would actually see is, I think there's a fuzzy blob there. We represent different colors in different ways to encode information in different ways. This is an infrared telescope. The JWST is an infrared telescope. So it's showing us invisible light. We have to turn that into something that we can really see. All right, so the main objectives of the Webb are to look at the solar system, planets that are orbiting the sun. We can learn stuff about planets that orbit other suns. We can learn about star formation, both locally within our home galaxy. We can see a lot of the details. We will be able to see a lot of the details. We haven't really yet. Details up close in our own Milky Way galaxy, and looking at star formation in other galaxies as well. That gives us a big picture view. We can also learn about the beginning of the universe, and that's the really exciting, that's the part I'm I'm excited about the exoplanets as a science fiction writer, but I'm also really interested in what it's going to tell us about the beginning of the universe. And most important for most people is it's going to make a lot of pretty pictures. The pretty pictures are not where the science is, but it's where the support for the program is. So there's a whole team of artists who work for NASA turning these images into the scientific images into pretty pictures. Jupiter. That's from space. It's only 1 million miles from the Earth. Okay, I'm an astronomer. I can say only 1 million miles. It's not too far away from us. 3 times farther away than the moon. 12 times farther away than the moon. We've got the great red spot, which is warm and glows brighter than its surrounding clouds. Galileo saw this storm back in 1610, and it's still raging. When Galileo first saw it, it was about 3 times the size of the Earth. Now it's only 2 times the size of the Earth. We've got some warm cloud layers, some cold cloud layers, aurora at the north and the south pole. Other storms, little storms, swirling clouds. These swirling clouds are the size of North America, Asia. That's beautiful. And the first picture of Jupiter's ring taken from Earth. All the other views of this ring that we've had are from the backside of Jupiter, looking towards the sun. You can normally only see this when it's being backlit. But it's a faint ring of dust that's orbiting Jupiter, and the dust is warm, and so it's glowing in infrared, so we can see it. There's also 2 of Jupiter's tiny moons. All right, so it can show us great views of objects in the solar system. We can also learn about planets orbiting other stars. If everything's aligned right, and it's not normally, I say, when the stars are aligned right, really good things happen. But in this case, if a planet is orbiting around the star so that the planet passes in front of the star from our point of view, the star gets a little bit fainter and we can detect it. The Kepler Space Telescope was working on that for 5 years. The successor to that telescope, TESS, is currently finding stars across the entire sky. And it's finding lots of planets out there. What the Webb can do is it can look at the star while the planet passes in front of it. And as the light filters through the planet's atmosphere, different colors will be absorbed depending on what elements and what chemicals and molecules are in the planet's atmosphere. So we will be able to, we've done it. We've measured the stuff that's in the atmosphere of another planet, a planet orbiting another star. This one, I think, is about 50 light years away. There's no way we're ever going to get here and do actual chemistry experiments, but by sampling the light, we can see there is water vapor in the atmosphere of this planet. That's not as exciting as it sounds. This is a gas giant. Gas giants have clouds that are made out of water vapor. But when we start looking at terrestrial planets, rocky Earth-like planets, we're going to see something similar to this, and we'll see water in the atmosphere of an Earth-like planet, which will tell us maybe there's life there. It could be possible. We have seen signs. I don't have a picture of it, but there was a paper published a month or so ago that found photochemistry going on in the atmosphere of a planet. Chemicals that are created by sunlight. Sunlight knocks apart some molecules, they reform and make other molecules in there. We've seen that happening. And so will we see some biosignatures in these other planets? Oxygen, free oxygen, O2, or ozone, O3. Those are produced by life. Oxygen has a short lifetime, it reacts with everything. So if there's a steady supply of oxygen in an atmosphere, something's got to be making it. It could be sunlight ripping apart water, but it could also be life. So we can find signs of life. And I've had a when I teach life in the universe, I have a bet that I try to make with students, whether we find evidence for life on a planet around another star first, or whether we find it on Mars first. And I am definitely on the exoplanet side. We're going to find evidence for life on a planet around another star pretty soon. We're not going to know anything about it, just that it's changing the atmosphere of its planet. And I am really excited about what this is doing. Yeah, so we can also detect, yeah, there's a little bit of carbon dioxide. This is the spectrum. This is in microns, 1 micron here out to 5 microns, so the really long wavelengths out here. Visible light is 0.5 to 0.7 microns. So visible light is right out here. So we're just looking at the infrared part. And this is called the near infrared because it's close to what we can see. And we've got some chemistry going on in the atmosphere of this planet. That's cool. So the star is just shining all by itself, and we see the light and the 3 different wavelengths. The short, these are all infrared colors, but the shortest wavelength we're calling blue, the middle one we're calling green, and the longest one we're calling red. And these are all mixed up together. But then when the planet passes in front of the star, it's blocking out the middle wavelength more than it is. You can see it easier down here. You're seeing more of the middle wavelength blocked than the longer or the shorter ones. So that's giving us, this is how we made the graph on the previous slide. Uh-oh. Let's go back. Come on. Okay. Guess I can't go back. All right. There we are. We've got a picture of an exoplanet. One of the great features that I was worried that was going to get cut out from the mission was there's something called a coronagraph. The sun's corona is the outer atmosphere of the sun, and we can only see it during a total eclipse when the moon blocks the sun. And then we can see its faint outer atmosphere glowing. We can't do that from the ground because if I put my thumb up to block the sunlight, there's still the sky that's drowning everything out. The Webb doesn't have that problem. It's in space. It can put up a little tiny disk to block the star itself, and we can see the faint things around it. There's some diffraction going on here. So this is just the single planet here. We've got a measure of how bright it is at a bunch of different wavelengths, which is really cool. So if we monitor this, we can look for if the planet is changing brightness. That's telling us about whether it's rotating or whether there's weather going on the surface. If it's a snowy day, that's going to be reflecting more light than if it's a hot, rainy day and it's a dark forest. So we might be able to get signs of weather going on these planets. Okay, so we can find stuff in the solar system. We can find stuff about other solar systems. We can look at how stars form. This is a star-forming region in the Milky Way. The Carina Nebula It's down in the southern hemisphere, so we can't see it from here. It's a giant star-forming region. There's a little bubble off to the side. And when you make stars, some of the stars you make are really large and really hot, and they glow. They're so hot, they glow in ultraviolet light. And that ultraviolet light excites the gas around it and makes it glow like a neon sign. And so the glowing here we have is hydrogen gas that's been excited by a couple of really hot, bright stars inside the cloud that's making it glow. So we zoom in on this piece, we zoom in on this piece, we zoom in on this piece, and here is a small region of the cloud where stars are forming. Inside here, that little tiny bug here, that's called an egg. Stars form inside eggs. They're like birds. Egg, EGG, stands for an evaporating gaseous globule. Okay. And yeah, let's go. All right. So here are two different infrared views of the same area. This one, where you can see the fuzziness in the background, that's the near infrared. See some features. This is the middle infrared. This part, this is the, I can't stop a GIF. This one is the starlight reflecting off of the surface of the cloud, and we're seeing what the cloud looks like in reflected light. It's blocking some of the light behind it. We can't see too much. This is the second image where you can see more stars. That is the mid-infrared. The cloud that the stars are forming out of isn't emitting infrared light on its own, and the cloud isn't blocking the infrared light from the stars behind it, so they shine through. And we can see more stars. All right, look down here. We can see into the cloud that's forming these two stars right here. Yeah, you can sort of see there's two stars in the other image. Oh, wow. We've got a view of them. This is awesome. Down here too, and over here. And yeah, even inside here. We've got it. I could just look at this for a long time. Okay, the Hubble was the largest telescope that could fit on the space shuttle. The Webb is even bigger because it's made out of segments, and there's folded it up origami style. And when it got into space, it unfolded and put itself together. So the mirror segments are hexagons. So we see these six-sided spikes are typical of the Webb images. All right, here is the Eagle Nebula, which is in the southern sky from Alfred. This is a picture with the Rosing telescope taken by Eddie Swain here. An absolute fantastic image. He took it last summer, and every week he comes back and is like, I made the image even better. And this is great. So it's not oriented in the way that shows what it is. So here's an eagle. We've got the eagle's body, its claws and its wings sticking out. Here's a group of stars that just formed. One of these stars, probably this one, is extremely blue and shining out a lot of ultraviolet light that's making this whole cloud glow. And here is a blob of really dense dust where star formation is still taking place. It looks dark because it's blocking the stars behind it. Never believe an astronomer when they talk about extremes. This is really dense dust. If you were to go here and open up a jar and collect a jar full of this dust, and bring it back to Earth, you would have the best vacuum we could produce. But it's light years thick. So really low density for light years is still going to block a lot of the light. When the Hubble took its first picture of this, Robert Silverberg, a science fiction writer, called this the most spectacular image anyone has ever taken. This is a cloud. Oh, these look like clouds. It is a cloud. They look like clouds. This could look like a thunderhead, except this is 20 light years long. We've got a hot star behind here, is making the backside of this glow, is making this cloud evaporate. But that little tiny spit there, there's a solar system forming inside that little spit. We got more eggs. Here's another one. There's one, there's one, there's one, there's one. There's one. There's a whole bunch of them on here. So this is the Hubble image of it. And you can see places where the gas is and dust is thicker and blocking the views. Over here as well. Here's the infrared view, the near infrared view. Here, we only have a hint of something happening here. It's like, yeah, there it is. There's something weird, different going on between here. We're not sure whether the thing is changed. This was from the 90s. This is from last summer. Maybe something's changed, or maybe there's something different. We're looking at a different section in the infrared. Oh, there's a hint of 3 stars here. There's way more stars. The starlight is passing through the dust mostly, and we're seeing all sorts of things. These blobs over here, you can almost see them. I just want to just stare at that forever. Right. Yes. This image was taken in the 90s, and this image was taken recently. So this is a 30-year-old image. Yeah. This is the mid-infrared. I didn't rotate it to give it the same orientation, but this image was released around Halloween. And that is a Dementor. That is a bunch of Dementors leaving, getting ready for doing something. There's just no other explanation. We got an egg forming stars. We got some more eggs. You can see the wispiness in the clouds. This is the light that the cloud itself is producing. It's slightly warm and it's glowing in the infrared, like the deer and the students and the computer monitor in that early image that I showed. Oh, and this one even has eyes. I can stare at that forever. Okay, so we can get a close-up look at star formation nearby. Nearby meaning 1,000 light years. Or we can look at star formation in entire galaxies. This is a group of 5 galaxies known as Stephan's Quintet. This is the Hubble image. This is the Webb image. This is the Rosing image. Orientation's different, but this is it again. One of the great images that Eddie got last summer. What we have here are 5 galaxies. 1, 2, 3, 4, 5. This makes up the quintet. Then we've got another galaxy and another galaxy. And I guess that's all we've got on this image. These 4 are the same distance away. I didn't look up the distance. Do you remember, Eddie? It's On the far side, so I'll say 20 million light years. This is a galaxy that is photobombing these other four. It's only 10 million light years away. So what we're looking at here is the combined light of 100 billion stars. Right? Carl Sagan was famous for saying billions and billions, and we got billions of stars here. Each pixel of this image is the combined light of millions of stars. All right, so here's the interloper. This red part is the glowing gas. And there's star formation taking place all around here. And we don't care about this one. What's cool is these four galaxies are interacting with each other. They are connected. These two are in the middle of a collision or a dance. Dance is better. These two are dancing directly, and that is causing the fluids from one galaxy to intermingle with the fluids of another galaxy. That's sounding a little bit. And when those gases collide, when two galaxies like each other, really, the gases collide, and we have star formation taking place right over here. We've got a tidal tail ripping back over here. There's all sorts of amazing stuff. This is going to put people who model these things inside a computer. This is going to give them years worth of work. The other spectacular thing about the Webb telescope is it can see more detail than any other telescope in history. Galaxies and galaxies and galaxies and galaxies. Every dot here, it looks like it's a galaxy. I could spend way too much time looking at that. Star formation here. Here's a galaxy from the New General Catalog. The New General Catalog dates to the 1800s. The General Catalog was the 1700s. Discovered by compiled by the royal astronomer for King George III. So here is the Hubble version of this. We have the central bulge, we've got the spiral arms, the dust cloud. This is the spiral arms, or where star formation takes place inside a galaxy. Here's the Webb mid-infrared view. The dust that's in here is glowing because it's slightly warm. Here, the dust, we can see it because it's blocking what's behind it. But when we line these two up together, this bubble here. So a star formed here a long time ago. It formed and it exploded, and the explosion traveled through space and blew out, emptied the dust from that region of the galaxy. And we see these bubbles left behind. We wouldn't notice it just from the Hubble view of it. But here it's like, whoa, there's a big empty spot, and star formation taking place along the rings. There's two different models about how stars form. One is with the spiral arms doing it all by themselves. One is the death of one generation of stars creates a new generation of stars. Here is more evidence for that second mechanism. Star formation is happening along the outer boundary of the explosion shock. Again, I'm just hypnotized by these images, and I will just stare at it. Okay, that brings us to cosmology, the really cool part. This is a Hubble image of a cluster of galaxies fairly nearby at 1 billion light years away. And the Hubble, it's cool. So there's a whole bunch of galaxies here. And there are some galaxies in the background. And the mass of this foreground cluster is enough to bend the light of the galaxies that are behind it. And it bends the light and it distorts it. So we see a bunch of little, oh, it's so much clearer here. Ooh, we have these rings. This is two galaxies that are behind this white cluster. And the gravity is distorting this and bending it out. The gravity is from the starlight we see and the dark matter we don't see. Don't ask me what dark matter is because nobody knows. We have no idea. We had a bunch of models that said it might be this, it might be this, it might be that. None of them have worked. We don't know what it is, but we can measure it. We know where it is. We know how much mass it has. We just don't know what it is. And so we can see so much more. Why does the Webb see so much more? The universe is expanding. The distance between galaxies is growing, but it's not just that the galaxies are moving away from us. Space itself is getting bigger. So the light that's traveling through the galaxy, light that was emitted as visible light, blue light, has been stretched by a factor of 10, maybe, for one of the ones we'll get at next. Galaxies, the lights, maybe the universe has doubled in size since the light was emitted. So what was emitted as blue light, the universe is stretched, and the distance between the peaks of the wave of light was also stretched, also doubled. So it was emitted as blue light, gets observed as infrared light. And so by looking at infrared light, we can peer back farther in time than anyone has ever done. Here's a close-up of it. Here's an extreme close-up of it. And again, I didn't time how long my talk was because I just kept staring at these images. Here's a really cool part. We can, by looking at the light, we can measure how much the light is shifted, and that tells us how far away these galaxies are. So this is from the first release. We picked up 4 galaxies. One of them is pretty far away. The light has been traveling towards us for 11 billion years. The universe is 13.7 billion years old. So this is light that's been traveling since the universe was 2-3 billion years old. Here's one. The universe is only 1 billion years old. 700 million year old universe. 600 million year old universe. Now, some people are disputing this, but we've got one galaxy, the faintest galaxy on here, and you can see all the static in the darkness behind it, was emitted when the universe was only 300 million years old. And again, I'm an astronomer. I can say only 300 million years old. This was the first image released. Maybe even if this one isn't right, it has the ability to see these things. We will be able to see the first generation of stars ever to form in the entire universe. And I'm giving myself goosebumps. This is just so cool. So the Webb has an amazing amount of things that it is going to discover. And we'll also be able to take more pictures with our telescope here, and we'll get really cool images. The next clues, the next things, we'll get answers about all of these things, especially what is dark matter. There's weird things about the expansion of the universe that I don't have time to go into, but we'll get clues about that. And this is such an exciting time to be an astronomer. I'll just leave this up here while I ask for questions. Thank you.
Thank you, David. If you've got questions, could I ask you to use the microphone for the Zoom test?
Thank you. This was awesome. When you were showing the cloud, the gassy cloud, and you said the stars light could come through it, does that mean this only the stars that are forming within the cloud, or even the stars behind it?
Everything behind it.
Everything
Everything behind it. Yeah, this is the same reason the sun turns red at sunset. The sunlight passing through the Earth's atmosphere, the blue light is scattered around all over the place. So only the red light is getting to us. So when we're looking at sunset and seeing the red sun, people in Hawaii and California are having the noontime sun shining down on them. In infrared, that's even more pronounced. So if we could see into the infrared, the sun would be, sunsets would be even more cool.
All this excitement about it, everything, and I'm personally worried for your mental health. If something goes wrong with the Webb telescope and it malfunctions and shuts down, whatever. Okay, do they build multiple ones at the same time? So the alternate can go up if there's a calamity like that? Is it?
There was a near disaster. This thing is floating in space. There's a lot of things floating in space. You know, one of the things I look at is asteroid collisions with the Earth. Micrometeorite hit one of the segments of the mirror. It didn't break it, but it was close. And that was just in the first 6 months. It does have a little bit of a screen to block stuff, but that is a potential disaster. And it will be very sad. This was built, funded in the 80s and the 90s, back when people thought they could get away with lowballing it, and then cost overrun. Oh, what do you know? Another cost overrun. The cost is doubling. The superconducting super collider, which was supposed to be discover the Higgs in this country, kept doing that. And finally, Congress said, no, we're not funding this anymore. So there's a giant hole in Waxahachie, Texas. It's not doing anything. Space Telescope Science Institute was trying the same thing, but Senator Mikulski, who's the senator for Maryland, was able to keep the funding alive long enough to get this up. And there were so many things that went wrong. Just before the first initial launch, they gave it a shake test because rocket launches are violent. And they gave it a shake test and pieces fell off. So they had to go 6 months of retightening everything and make sure it was going to survive. I did not get up early Christmas morning to watch it, but I wasn't going to believe it was working till it actually cleared the atmosphere. It did. No. Mars probes, yeah, they do that with Mars probes so they can test out. Let's see if this is, they have a model to test it on and do experiments with to figure out what's wrong. No, with a $10 billion thing, we're not making a spare. Even though it's only a quarter of a Twitter.
David, I have a question. Could you go back to the slide of the clouds?
Maybe.
Does it go in reverse?
Ah.
Yeah, that.
Top one or the bottom one?
That one. Yeah, my question is, clouds on Earth kind of move, and are they able to detect movement at all in these clouds, or is the time scale too great?
This is 20 light years. The gas is moving 1,000 miles an hour. 1,000 miles an hour to go a light year is gonna take you a couple thousand years. So to look for change, maybe this is a tiny change in here. Maybe something is breaking through. But the size is so huge and the speed is so slow that unless we get extreme anti-aging technology so that people live for 1,000 years, we're not going to see that in most astronomical images. There's one cool exception for that. The Crab Nebula was a supernova that exploded in 1054 AD. The Chinese saw it, mapped it in the right spot in Taurus. And if you look at pictures taken 50 years ago with pictures taken now, you can see it expanding. And you can measure the expansion rate and figure out that it was zero size back around the year 1000. That's sometimes lab we do in astronomy lab, if it's on a cloudy night.
We are past 1 o'clock. Anyone have a question just dying to ask? If not, we can finish, and by all means, come to the front and David will answer more questions then. But thank you again, David. Wonderful.
All right, thank you.